Hi guys, time flies. It's been over a year since I created this channel. Thanks for watching anyway. And we've covered a lot. Subatomic isotopes, chemical bonds, Lewis diagrams, electron energy levels, isotopes, nuclear chemistry, electronegativity, neutralization polarity, and more. I figured we need something a little more interesting and useful. We'll talk about LEDs as an Xmas special. Now you'll finally understand the little tender lights you put on that tree. LED stands for light emitting diode. Before we talk about those cute little contraptions either, enter the diode. That's the important part of electronics that makes sure you don't plug the battery in the wrong way and make it do all sorts of ridiculous stuff. Even before we explain its lineage to our LEDs, I must tell you how diodes are made. We start with a metal mixture, normally indium gallium nitride. Indium gallium nitride is a crystal of bonding alternating indium or gallium cations and nitrogen anions. At this point, all the electrons are used in bonding, so it's actually a terrible conductor. Sorry. Then we insert a couple of atoms that will create some intentional mistakes in the bonding structure. Indium, gallium, and nitrogen form 4 bonds, but if you add some phosphorus in, there will be some extra electrons on the phosphorus atoms, which need somewhere to go. On the other side, we add some magnesium into the mixture. These guys also act as indium or gallium. However, they only carry 2 valence electrons with them, blowing their cover. Nitrogen anions expect 4 electrons, but find only 3. This makes a hole in the crystal. As the electrons move into a hole, they also leave out a hole. The hole then appears to move around, like a mobile positive charge. Now comes the matter of naming these hole-filled or electron-filled materials. We call them N-type and P-type. The material with holes are P-type for positive, and the material with extra electrons are N-type for negative. Well, what happens when you put them together? Exactly nothing happens. To explain this, we have to look on the inside of the atoms. Phosphorus has an extra electron in itself. As it is forming 4 covalent bonds as well, this effectively puts a positive charge on the atom itself. Boron has the opposite going on. It has a negative charge on itself. So at the junction between the materials, the electrons and holes are pulled back by their own atoms. This makes the material not conduct electricity, and it is useless for electronics. But, and this is a big but, if you give enough voltage or energy on the electrons, they can force their way through the junction. Well, isn't that just a normal conductor? No. If you plug the battery the wrong way, the voltage would also be applied wrong, and the electrons and holes would be held away tighter than ever. This causes the material to conduct even worse. So now you have a component that conducts electricity if you plug in the battery one way, but not the other. That's a diode. However, if we want to make that diode shine, we have to dig deeper into and that's why bands exist. Now, electrons can be in either the conduction band or valence band. If an electron is being bonded, it's in a valence band. Extra electrons are in the conduction band. Since holes are the emptiness of electrons in bonding, it exists in the valence band. When an extra electron fills a hole, that electron jumps from the conduction band into the valence band. So it moved from higher energy state to low energy state. Well, where'd that energy go? You guessed it, the light emitted by the LED.